Welcome to Lecture 13 of Electrical Engineering 525. We will begin today's lecture by finishing up Section 3, which is about the Yagi Uda antenna arrays, and then we'll move on to Section 4. So the last problem that we want to look at today, or in this lecture, for the Yagi Uda antenna arrays is problem 6.3-8. Which reads as follows. A two-element Yagi has a current on the driven element of 1 at an angle of 164 degrees and a current on the parasitic element of 0.5 at an angle of 238 degrees. The spacing between the elements is 0.2 lambda. Does the parasitic element act like a director or a reflector? So let's first of all make sure we understand the geometry of this problem, and then we'll begin to discuss how to solve it. So here is the driver element, and here is the parasitic element. And I would suggest that on any problem of this type, you go ahead and set up the driver as the leftmost element and the parasitic element as the rightmost element. Now again, I'm only saying this for problems like this where you have a two-element Yagi and you're asked this kind of question. Otherwise, the situation may be different. For instance, we've already considered some problems where we had parasitic elements on either side of the driven element, but in a case like this where we have just a two-element Yagi, obviously we only have two choices. Either the driven element can be to the left of the parasitic element, or it can be to the right of the parasitic element. So let's just go ahead and, for the sake of consistency, always keep, in this kind of a problem, we'll always keep the driven element to the left of the parasitic element. So you might say, with respect to the driven element, the parasitic element is in the theta equals 0 degrees direction. We're thinking of, as in our previous problems, we're thinking of this as being the z-axis, and so the parasitic element is relative to the driven element. It's in the positive z direction, or in the theta equals 0 degree direction. And then, of course, the opposite direction would be the theta equals 180 degree direction. So here's our driven element. Here is our parasitic element. The distance between them is 0.2 lambda. The current on the driven element is 1 at an angle of 164 degrees. The current on the parasitic element is 0.5 at 238 degrees. If we call this separation distance d, which is 0.2 lambda, we already know from our previous problems that if we're going to try to find the pattern in the theta equals 0 degree direction and in the theta equals 180 degree direction, we're going to need to know this the value of this quantity beta d. So let's go ahead and calculate it right now. Beta d, beta is 2 pi over lambda. D in this case is 0.2 lambda. So the lambdas cancel and we get 0.4 pi, and then we multiply that by 1, written in the form of 180 degrees divided by pi radians, and the two pi's there will cancel. And of course, it's understood here that this 0.4 pi is in radians, so the radians there will cancel with radians here. We get a final answer in degrees, and it will be 0.4 times 180 degrees, or 72 degrees. And now we're ready to proceed with this problem. And basically, this is an easy problem. It boils down to this. Again, the question is, does the parasitic element act like a director or a reflector? Well, if we calculate the pattern in both end fire directions, in the 0 degree direction and also in the 180 degree direction. And if we find out that the maximum is in the theta equals 0 degree direction, the maximum amplitude, then this parasitic element is acting like a director. It's directing the wave from this driven element in the direction that the director lies with respect to the driven element. In other words, the parasitic element is here to the right of the driven element, and it is directing the wave to the right. That's our conclusion if the amplitude here in the 0 degree direction is larger than the amplitude in the 180 degree direction. On the other hand, if we find that the amplitude over here in the 180 degree direction is larger than the amplitude in the 0 degree direction, then this parasitic element must be acting as a reflector, and it's reflecting the wave that comes from the driven element back in this direction. So that's the idea of how we will solve this problem, is simply to compute the magnitudes in both end fire directions and then compare them. But there's one other interesting point that will arise as we go through this problem. So let's see how it goes. Okay, well, the analysis is exactly the same as what we've already done. If we're looking for the pattern in the 0 degree direction, then we have the pattern. We have the field of the driven element with the phase shift, because we want to evaluate that field here at the parasitic element, and so that's 1. And then the angle is 164, but then we have to have the beta d phase shift, so that's minus beta times 0.2 lambda. And we add to that field the field of the parasitic element at the parasitic element, which is 0.4, an angle of 238. So we bring that down here. Now we've already calculated that beta d is 72 degrees. So this is 1 at an angle of 164 minus 72, and we just bring down this term. So this is 1 at an angle of 92 degrees plus 0.5 at an angle of 238 degrees. And if you do that calculation, and as we have mentioned in class, hopefully you have a calculator or access to an app that will allow you to add these two phasors directly without having to break them up into their rectangular components and then adding the components separately and then putting it back into polar form. This is much, much easier if you have access to an app that will allow you to just add these phasors directly. But anyway, however you do the calculation, you should come up with pattern in the theta equals 0 degree direction of 0.65 at an angle of 117.5 degrees. Now let's calculate the pattern in the theta equals 180 degree direction. So again, referring to the figure here, we have the field of this driven element, which is 1 at an angle of 164 degrees. And then we also have the field of the parasitic element, which will be 0.5 at 238 degrees, but then we once again have to subtract the phase shift, which is 72 degrees. So this ends up being 1 at an angle of 164 degrees, plus when we say 238 minus 72, we get 166 degrees. So this is 1 at an angle of 164 plus 0.5, an angle of 166. And this will give us a total, a final answer of 1.5 at an angle of 164.7 degrees. And so we notice that this the magnitude in the 180 degree direction is substantially larger than the magnitude in the 0 degree direction. So we conclude in this case that since this magnitude is greater than the magnitude in the 0 degree direction, the parasitic element is acting as a reflector. So that's all there is to that problem. But there's one other thing to note here that's interesting. Notice that when we calculated the pattern in the 0 degree direction, after we included the phase shift, we came up with one phaser here at an angle of 92 degrees and another phaser at an angle of 238 degrees. Now these two angles, these two phasers are not, you certainly wouldn't say that they were in opposite phase of each other, because for that to be the case, then they would have to have a 180 degree difference between them, and there isn't a 180 degree phase difference between them. But on the other hand, they certainly aren't in phase either. But on the other hand, when we looked in the 180 degree direction, notice that the angles are 164 degrees and 166 degrees. So in that direction, these two phasers are almost exactly in phase with each other, and so it's not surprising at all that we come up with a much larger magnitude in the theta equals 180 degree direction than we do in the theta equals 0 degrees direction. So sometimes just by looking at these phases, you might be able to predict the answer without going ahead to the final answer. But of course, again, if you have access to an app that adds phasers, then it's a trivial matter to just go one more step. So that concludes the problems from section 6.3 on the Yagi Uda antenna arrays. And certainly, we've spent 2.5 lectures on this, which is just representative of the fact that it is an important topic, largely because the Yagi Uda antennas are very practical and widely used. So now let's discuss the first group of problems in test 13 before moving on to section 6.4. So for test 13, we're going to have the situation described in problem 6.3-9. Now again, the problem that we just were discussing was problem 6.3-8, but the problem we're going to consider in this first group of problems on test 13 is problem 6.3-9. However, this problem is almost identical to the one in 6.3-8. The only difference is described here. So it says same situation and spacing as above. So in other words, the spacing is still a 0.2 lambda, but the driver current is 1 at an angle of 254 degrees in this case, and the current on the parasitic element is 0.6 at an angle of negative 32 degrees. So the first problems on test 13 will be dealing with that situation. And again, that's the same situation as we have in problem 6.3-9 of your textbook. So now we go to section 6-4, which is on the feeding of wire antennas. And we have just a couple of relatively easy problems on this to get the idea of the material covered in this section. So it says in the first problem that we're going to consider, which is 6.4-1, a receiving antenna with a real impedance R sub L attached to its terminals has the equivalent circuit shown. And right down here, we'll talk about it in a moment. Prove that the maximum power transfer to the load for a fixed antenna impedance R sub A occurs for RL equals R sub A. So the idea then is here is our antenna over here on the left, and here is its impedance R sub A, and the voltage that falls across the terminals. Well, actually, This isn't exactly the voltage across the terminals of the antenna because there's going to be a voltage drop across RA, but this is the voltage associated with the currents on the antennas. We'll say it that on the receiving antenna. We'll say it that way. And here is R sub L, which represents some kind of load which is attached to this receiving antenna. So again, this is a receiving antenna. It's one that's going to receive a signal from elsewhere. And because of that, that's how this voltage is induced on this antenna. So we want to show, we're assuming that this, the impedance of the antenna, R sub A, this is fixed. But we can change the load resistance. And both of these, by the way, are real. This is R sub A is real, and then we are assuming that we have a real impedance over here as well in this problem. And so the question then is, what should our choice be, our choice of R sub L be, to get maximum power transfer? And of course, you've done problems like this in circuits before, so this I don't think will be hard for you at all. But let's go over it just to remind you of how it goes. So if we call the power transferred to the load P sub L, then well, the power transferred to the load, of course, is I squared R sub L. Now, the current I will be V, the voltage here, divided by the total resistance, R sub A plus R sub L. So we have I squared R sub L is equal to V over R sub A plus R sub L quantity squared times R sub L. And then when we square what's in the parentheses there, we will get P sub L. The power transferred to the load is V squared times R sub L over the quantity RA plus R sub L squared. And now that we have this expression for the power transferred to the load, we want to maximize the expression. And of course, the way we do this will be to calculate the derivative of it with respect to R sub L, because remember, R sub L is what is varying here. RA is fixed, but R sub L is varying. So we want to differentiate this expression with respect to R sub L and then set it equal to 0. So if we do take the derivative of this with respect to R sub L, then we get, since we have R sub L in both the top and the bottom, we need to use the quotient rule. So here we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now keep in mind that the denominator here is the quantity RA plus RL squared. So you can think of this as U squared, and of course the derivative of U squared is 2U times du dx. We're differentiating with respect to x. When we're differentiating with respect to R sub L, we get 2U du dr sub L. And of course, if this is U, then the derivative of that with respect to R sub L is just 1. So we just end up here with 2U, or 2 times R sub A plus R sub L. So that explains the numerator. Again, we have the denominator times the derivative of the numerator minus the numerator right here, V squared RL, times the derivative of the denominator, 2 times the quantity RA plus RL. And then when you use the quotient rule, the denominator term is denominator of this original term squared. So we have RA plus RL squared, or RA plus RL to the 4th. And now if we multiply the top and bottom of this by 1 over RA plus RL, then the RA plus RL squared becomes simply RA plus RL. This RA plus RL will disappear, and the RA plus RL to the 4th in the denominator becomes RA plus RL cubed. Again, what we've done there is just to multiply the top and bottom by 1 over RA plus RL. So then we get this slightly simplified expression here, and we're ready now to set that equal to 0 to find out the condition that gives us maximum power transfer to the load. And when we set that expression equal to 0, then that occurs when the numerator is equal to 0. So we go ahead and write that down. The numerator is RA plus RL times V squared minus 2V squared RL. And we set that equal to 0. Then that bring this term over to the other side of the equation. And we get this. And of course, you can see here that the V squareds on both sides will cancel to give us RA plus RL is 2RL, which of course implies that RL is equal to RA. So indeed, the maximum power transfer occurs for RL equals RA. Now in the second problem from this section, 6.4-2, it is dealing with a transmitting antenna. So it says a transmitter with a real impedance of R sub t is connected to a lossless transmission line of real characteristic impedance R naught, and then to an antenna of real input impedance R naught. And part A of this problem is derive an expression for the transmit efficiency. That is, power delivered to the antenna divided by total power delivered by the transmitter. Neglect any mismatch effects. So in order to derive this efficiency, let's first, again, as we did in the previous problem, let's start with a picture so we make sure we understand what's going on. So here to the left of this first pair of terminals is the transmitter. And here is RT, the impedance of the transmitter, as was mentioned in the problem. Here, between the left set of terminals and the right set of terminals, we have a lossless transmission line of characteristic impedance R naught. And then finally, we have our transmitting antenna, which has a real input impedance of R naught. And we want to calculate the transmit efficiency of this, which is the total power delivered here to the antenna divided by the total power that is being delivered by the transmit source here. Now it's important to realize this transmission line is lossless, so no power is being delivered, no net power is being delivered to the transmission line. And furthermore, let's talk a little bit about this statement, neglect any mismatch effects, since the characteristic impedance of the transmission line is R naught, and the input impedance of the antenna is R naught. That's why we would expect to have no reflection of energy from the antenna back to the transmission line. So